I can see your slides.
Okay, great. You see just a title slide, nothing else, right?
Yes. Yeah.
Great, great. Last time we brought this to the committee, it was called Must Fail Fast, and it got stage 1, and then it got blocked from advancing from there for reasons I will explain. And this is a stage 1 update. Since then, we renamed the proposal Don't Remember Panicking. So I'm going to linger on this slide for a little bit because this is the code example I'm going to use throughout the entire talk. So it's worth all of us getting oriented in this code example. This is a simple money system. Don't worry if you spot bugs. It's purposely a little bit buggy, which is in order to illustrate some of the points. At the top here, this is just a validity checker. It's a NAT that takes a number, and if the number is a natural number, i.e. non-negative, it returns it, otherwise it throws. The instances of class purse each represent a holder of money such that money can be moved from one purse to another. This money system has exchange rate conversion built into it. So for each purse, there's a number of units of some currency, which is the variable field, and then there's a unit value, which is how much is each unit of that currency worth in some quantum unit of currency, some fine-grained quantum unit of currency. And we use the NAT on construction to ensure that both of these are non-negative. And all of the action, everything interesting is in the deposit method, because the deposit method is there to implement transactional totality, that all the effects happen or none. The effects are that we're moving my delta units into this purse, the destination purse, withdrawing the worth of those units from the source purse. And we're trying to keep the total worth approximately conserved. So this is implementing the transactional totality using the prepare commit pattern, which I do recommend. And the prepare commit pattern has a prepare phase that provides the none of the all or none, which is it's doing all the input validation, all the precondition checking, such that all possible throws or early returns happen here, and in particular, no effects happen here. So if you throw or early return, no damage has been done. And this particular prepare phase checks that this is an instance with this dot sharp here, that this is an instance of the purse class, that source is an instance of the purse class, that my delta, the units, the number of units we're transferring into this purse, the destination purse, is non-negative, and this outer NAT here with the two multiplies and the subtract is checking that source would not be overdrawn. So if any of those are reasons to bail out early, we bail out early, not doing any damage, and otherwise we go past the commit point into the fragile phase. The fragile phase is a thing that implements the all of the all or none, which is that once you start into it, you're performing effects, and the correctness of the system depends on all of these effects happening, that there is no bailout in the middle here after you've started to perform some effects. Okay. So in JavaScript, the JavaScript spec does not admit the possibility of out of memory or out of stack. But if, for example, the numbers we're computing with here are big ints, then even a multiply allocates, and depending on how it's implemented, even with floating point numbers, a multiply might allocate. It also might need a new C stack frame. And anytime there's an allocation, there's always the possibility that there's no more memory to allocate, or that you're out of budget for the total stack space or total number of stack frames. And because this can happen anywhere, and the possibility is not part of the acknowledged semantics of JavaScript, it's just unreasonable for the programmer writing something like this to have to think to be defensive against errors like this. If they happen, then, well, in this case, if it happens, then the destination purse, this purse, its units were incremented, but the source purse, the one that its units were not decremented because of this failure. So you could think that, well, maybe the programmer should just be defensive in general in the fragile phase by putting it into a try-catch, which makes a lot of sense, except that if the programmer has no idea why this block might have failed, maybe it failed in the plus equal here rather than the multiply, if they don't know why it failed, and without an extraordinary amount of extra bookkeeping to consult, they have no idea what to do to repair the damage. That at this point we have unknown corrupted state, and to proceed with execution with unknown corrupted state is to compute forward with corrupted state and continue to do damage. And since we don't know what's corrupted, we don't know what further damage will happen. So this is not a tenable situation. So what the first version of this proposal was exclusively about was such out of memory or out of stack policies. And what we were advocating is that when such an exception, such a problem state happens, such a fault happens, that the agent exit immediately. The agent immediately terminates because any further execution of JavaScript code after this point is just too dangerous. However, when we presented this, we ran into the objection that from browser makers in particular, that browser makers currently do throw on the out of memory, and they were unwilling to change that as the default policy because there's too much code out there that counts on being able to continue after such things happen. I'll explain why that's, in slides coming up, why that's actually quite a sensible policy, especially given the view of JavaScript when the browsers arrived at that policy. So instead of proposing that it be a part of the JavaScript spec that we immediately terminate, we're instead proposing that the decision, the policy decision, is delegated to a host hook. And the host hook, we're generalizing it from just out of memory and out of stack to a bunch of different faults where you provided a fault, we provide the host with the fault type and an argument that can provide additional information per fault type. So in order to make sense of this, we need a taxonomy of fault types. Wrong taxonomy, those are earthquake faults. Let's go to software faults. So after unrepairable corruption has happened, the most important part of our taxonomy is that it's not possible to continue with both availability and integrity. You can't compute forward from unrepairable corruption, preserving both availability and integrity. So one possibility, one possible choice for the host is fail stop, which is to sacrifice availability for integrity. That's certainly what you want for something where you want transactional totality, like a money system, where user assets are at stake. But what the browsers expressed as their desire for the default policy is what we would instead call best efforts, which is to sacrifice integrity for availability, to remain responsive. And so remember that the browsers arrived at this behavior during the ECMAScript 3 days or earlier. I arrived at the committee during ECMAScript 3 when the entire language is what we are now calling sloppy mode, in which even a failed assignment, you would just continue past the failed assignment silently, going on to the next instruction. And the reason for that was the engineering goal, the view of JavaScript and browser behavior at the time, is the most important thing was to preserve availability of the page, to preserve that the page stayed interactive, even if the price of that was to compute forward with corrupted state. So the next part of our taxonomy is these 4 levels of severity of a software fault. So the first level of severity is that, and now I'm being a little sloppy with the word host. I mean host or JavaScript engine, but not JavaScript code. This is the code that implements what JavaScript code sees, that it detects that its internal state is corrupted. For example, an internal assert is violated. I'm just guessing here that the browsers have something like an internal assert as well. I've only studied the internal faults for XS, and I'm guessing about the browsers. But if the internal state of the host or JavaScript engine is corrupt, then I'm assuming that we all agree that those cases do call for fail stop. And in the browser, we see the blue tabs of death for XS, which is meant primarily for devices. There's the quite sensible policy of just rebooting the device, not computing forward with corrupted state. And they've found that to be a much more robust way to continue. And for XS, the out of memory and out of stack are in this severity category, because the XS machine is not built to guard its own integrity against these conditions. The browser engines, we're guessing, based on the objection previously raised, that they are built so that following out of memory and out of stack, that the JavaScript engine and host have not lost their internal consistency, that their internal invariants still hold, but they're now in a position that they cannot continue executing JavaScript while upholding the semantics of the JavaScript spec. So the error that they throw is an error that is outside the JavaScript spec. And because it's outside of the JavaScript spec, it's outside what the JavaScript programmer thought they could count on. And therefore, we should assume that the JavaScript code is now continuing to commute with its state corrupted, even though the C state, so to speak, is uncorrupted. So at this point, so for this severity level, it makes sense for the host to decide between best effort and fail stop, depending on whether integrity or availability is the overriding goal. But if a host chooses fail stop, we think that it should provide some API, and we're not proposing what the concrete API for this would be, but if the default policy is best efforts, we're advocating that the host provides some API such that the JavaScript code can opt into fail stop to protect itself, such as for such banking examples. And in fact, we would propose that whatever this API for opting into fail stop is becomes standardized as part of JavaScript. Okay, the next lower severity is the host is fine. The JavaScript, the host can proceed within the JavaScript spec, but something happened such that we can think of the JavaScript code itself as likely being in trouble. There's some symptom that we know about that the host can react to based on the assumption that it indicates that the JavaScript code might be in trouble. So unhandled exception, unhandled rejection are the well-known ones. There's also for XS has metering built in such that it can be out of time. The browsers, in order to cope with an infinite loop happening within JavaScript code, might time that out and then have some strategy for continuing execution if that times out. And then the next lower level of severity I will come back to. But let's, at this point, to motivate that remaining level of severity, let's go back to our example. So now that we're familiar enough with this code as a whole, let's just scroll forward to where we see both the deposit method and some code for testing it. So there is an obscure bug in this code, or maybe not so obscure to some of you, but the nature of this bug is such that it could survive zillions of test cases like this. It might survive during development and review and test cases because it requires a weird data coincidence in order to reach the bug. So the result is that that data coincidence might happen first in deployment at a customer site, having survived development and testing. And the data coincidence is shown over here, where it happens if we're providing it big ints rather than numbers, and that there's a 0 here on the unit value of the source purse, which is not something that that the developer might have thought to try, and a 0 in the amount in the destination purse of the amount we're trying to increment the destination purse by. If there's a 0 in both of these positions, then this divide operation will throw a range error, and if we continue computing past that throw, then because we never noticed the possibility of this bug during development, we now again have corrupted state in deployment in a user code, in a customer site, which is really bad. And we might again try to do something about this by putting a try-catch around it. But again, if we don't know what the problem is, we don't know what to do to repair the state without extraordinary amount of extra bookkeeping. So the most we can do is log it, or try to do some kind of log of diagnostic that ultimately makes it back to the developers, so that at least we know why Zalgo is laughing at that point. Now, surprisingly, there actually is a way in JavaScript today for this code to defend its own integrity at this, and to sacrifice availability to preserve integrity, at least as far as the spec is concerned, which is it can go into an infinite loop at that point. And as far as the spec is concerned, that blocks all further execution in this agent. Zalgo never gets to observe the corrupted state, never gets to do damage because of continued commuting with the corrupted state, and we're safe. But there's two problems with this. One is the price of this safety is very expensive, and it's expensive for the customer, since this happens first at a customer site. And the other one is that if the host already has a policy that it engages in some remedial action like a throw or aborting the current turn, if it times out, like we believe the browsers do, and then continues execution, then that leaves the semantics of the JavaScript spec, and then continues computing anyway with corrupted state. So what we're proposing instead is that the JavaScript code have some way to say, "Somebody stop me," which is this reflect.panic operation, which is new API that we are proposing, so that it can become a practice when engaging in the prepare commit pattern to do a try catch, and then to stop the agent, to abort the agent, as soon as possible. As soon as the assumption with the fragile block is that no early exits happen here. So if an early exit does happen here, that's enough of a symptom to say, okay, we violated our basic assumption of a fragile block. We don't know how to repair the damage. Just terminate immediately. Another thing to do with the reflect.damage is that, and in turn, the JavaScript code itself can now just do a assert-like operation, whereas current asserts might throw an exception, throw an error, when the assert condition is violated. A more severe JavaScript code might say that, well, if this assert gets violated, I have no idea how to continue, so just panic at that point. So that brings us to the remaining, the next lower integrity level, which is the JavaScript code notices its own corruption through a failed JavaScript level assert or an exit from a fragile block, calling the reflect.panic, which in turn calls the host fault handler with the fault type user panic, and then whatever arg is provided here becomes the extra data provided there. Now, throughout this talk to this point, I've been saying repeatedly, abort the agent. But there's been a conversation on this whatwig thread in the HTML repo going back to 2017 on 3 different bug threads, including a new bug thread as of a few days ago, of what the actual unit of computation is that needs to be aborted when we need to abort this, what we're calling in this talk, the minimal abortable unit of computation. And what these are discussing is do we have to abort an entire agent cluster? So a way to visualize the dilemma is agents, before the introduction of shared array buffers, the agent was indeed the minimal abortable unit of computation, because objects within an agent could be were indeed synchronously coupled to each other, and in general, computation within an agent is synchronously coupled to each other. So you would have to abort at least the agent, but back then, agents were only asynchronously coupled to other agents, so you could abort an agent, and then other agents were in a position to react to the sudden absence of an agent they had been talking to. With the introduction of shared array buffers, agents could be synchronously coupled to other agents. So the agent cluster, which is what those HTML threads are about, is what we're in this talk calling the static agent cluster, which is all of the agents that might be synchronously coupled to each other because they might share a shared array buffer. So that is certainly a sound unit for jointly aborting, but it's not really satisfying as the minimal unit because there can be a tremendous number of agents within the agent cluster, and sacrificing all of them to preserve consistency seems unfortunate. So fortunately, there is a smaller unit to abort, which is what we're calling here the dynamic agent cluster, which is at the moment the fault happens. Let's say the fault happens within this agent. If the fault happens within the agent, then at the moment of the fault, first of all, the processing of the fault is clearly something that can be on the slow path. Nobody cares how long it takes to kill a bunch of tabs. What we can do is if the fault happens in that agent, we can say at that moment, what is the transitive closure of agents synchronously coupled to the agent in which the fault happens at that moment, and then kill the transitive closure of those agents, the ones that are in that agent cluster. So this one would also be killed, but this one would not be killed, even though it's in the same static agent cluster. So the assumption that we're making in providing this host hook that can choose to abort this minimal abortable unit is that it is allowed for this new host hook to not return control to JavaScript. However, the actual text of the spec says something that in fact JavaScript engines generally violate, which is that the host hook must return either with a normal completion or a throw completion. Instead, host hooks, instead execution today, depending on what goes wrong, might core dump or produce some other kind of diagnostic snapshot, depending on the host. On node, process.exit, which granted is not actually a host hook, but is just a host provided built-in, process is a host object, does not return control to JavaScript, and of course the browser blue tabs of death. So we want to acknowledge that by allowing in particular the host fault handler not to resume JavaScript execution. All right, hold on. But there's actually another way to not resume other than simply death before confusion. It's certainly the case that you can't resume by simply allowing computation to proceed forward, but one of the reasons why the browsers do the blue tab of death, preserving the URL in the URL bar, is to give the user the choice to just refresh the page. The host hook could conceivably just decide to have refreshed the page on its own, although I don't recommend it. I think giving it to the user choice is more sensible. But in any case, the reason why refreshing the page, whether at the browser's choice or the user's choice, makes sense is that you're falling back to a previous consistent state. You're immediately forgetting, you're abandoning all of the corrupted data state. You're abandoning it immediately, no further damage happens, and you're falling back to a previous consistent state. XS, in rebooting the device, does exactly that. The previous consistent state is the state in ROM. A friend of mine who is doing an extremely reliable operating system one day was talking to somebody who does the software for pacemakers, which clearly need to be extremely reliable, and asked them, okay, how do you deal with various kinds of fault that might happen in your own pacemaker software? And he said, the heart is an extremely fault-tolerant device. It can meet a beat or two without much worry, so we just reboot the pacemaker, and that works. And by rebooting, you restart from exactly this previous consistent state that's in ROM. But if it took 10 beats to reboot the pacemaker, that would be a very different story. At that point, you might prefer best efforts. And then Agoric does a full transactional abort, which is between transactions, Agoric has stored enough snapshot and log information that we can completely abandon the corrupted state, the state of the aborted transaction, and restore from previous consistent state, and then continue to compute forward from there. So this kind of amnesia before confusion is a way to preserve both availability and integrity. This policy of providing this kind of abort of this minimal abortable unit supports hosts that want to have some kind of fallback to a previous consistent state. So that brings us to the larger question of how one builds fault-tolerant systems and what fault-tolerant systems are trying to survive. So there's the conventional dichotomy of building fault-tolerant systems out of Byzantine components versus fault-tolerant systems out of fail-stop components. And usually this is discussed in the context of hardware faults, where the hardware faults are assumed to be non-replicated so that you can have multiple replicas running the system that where the fault occurs in a minority of the replicas. So with Byzantine faults, it's assumed not to fail stop. It's assumed to continue forward computing with corrupted state and therefore be unpredictable. And furthermore, more generally, a Byzantine fault means that the individual piece of hardware might indeed be malicious, which is the assumption behind Byzantine fault tolerance and blockchain. And this is hard, but there's zillions of systems now that do exactly this. And that copes with the supply chain risk where some of the hardware running the computation might indeed be malicious. And then there's just the more common hardware assumption that you can build the hardware to act in a fail-stop manner, and then all you need is simple redundancy in voting. That is represented by systems like the tandem nonstop, where the replica that loses the vote just drops out. Also, various failover schemes are essentially in the same category. But there's the more interesting category of failable applications. What if there's a bug in the code? Or what if there's a fault in the interaction of the user code, the application code, and the software that the application code is running on, where all of the replicas are running the same software, in which case any of those faults are replicated. And if they're replicated, the hardware redundancy is of no help at all. We have to engage in other coping mechanisms. So what Agoric has certainly been focused on mostly is replicated faults that are Byzantine faults, which are, for example, library supply chain risks, where a library itself that's linked into your software might be malicious. And now we can't mask those errors, but we can reduce the severity of those those faults with principle of least authority, providing the library with no more ability to cause effects than it needs to do its legitimate job, which is often tiny compared to the status quo of what's provided to libraries today. Object capabilities, defensive consistency, where individual components are programmed to maintain their own consistency in the face of malicious callers, and compartmentalization, which is what the compartments proposal was about. But today, what we're raising is this other category of application faults, which are where the faults are not malicious, and we would like to make the faults into fail-stop faults so that we can do fault containment. And this is what the Erlang philosophy is about with Erlang supervisors. Erlang uses the phrase fail-only programming, meaning that an Erlang process, which is very much like our agent, or if something goes wrong, it terminates immediately, and it leaves it to other agents, including an agent serving as the supervisor of the agent that fails, but in general, other agents interacting with the failed agent, to react to the sudden absence of the failed agent. And that fits with the postmortem philosophy that we followed when we introduced weak references and postmortem finalization, which is, as opposed to the Java finalize method, which is a method on the object being garbage collected, which is if you're being torn down or if you're confused, you're the last one that the system should ask to cope with the consequences that you're about to go away, because you're confused. You're the least capable of being able to cope correctly with your own corruption. Rather, we should just kill you immediately without consulting you, and then let other code elsewhere deal with your sudden absence. And so that we're doing that for garbage collection with postmortem finalization within an agent, and we're proposing with these panics and fault handling to be able to apply that to the agent as a whole with other agents reacting. And that brings me to the end of this stage 1 update. And now I will take questions after turning recording off.